In this session I'll finish off the discussion on tunneling, and then I'll introduce a really important new topic in quantum mechanics on the nature of multi-particle systems, because it's really there that the true weirdness of quantum mechanics arises. Well, I mean, superposition is pretty weird. So by my tastes, I put my choices for the two weirdest phenomena in quantum mechanics. One is superposition. It's almost unimaginable classically. How can you be in two places or going in two opposite directions at the same time? That kind of thing. And the other one is non-locality. But non-locality, you can only even describe it once you have a fairly good knowledge of the quantum mechanics of multi-particle systems. So in this course we will not discuss non-locality. I've just been mentioning it as sort of a foretaste for next level. So if you follow me up to Masters 1, so M1 level, where the text that we'll be using is this one by Mandel, just called simply Quantum Mechanics, and he has a section, quite a decent section in this book on Bell's inequalities, and that's all about non-locality or entanglement, which is the same thing. The physicists tend to call entanglement non-locality, and the computing guys tend to call non-locality entanglement. So just two labels for the same phenomenon. Alright. Okay, so just this little section here finishing off tunneling. There's still a few surprises. So now let's do the other case where the energy E of your incoming free particle, that E is actually larger than the potential. So E is greater than V naught. Well, in the previous session we had expressions for big T and big R, so the transmission fraction of your the square of your amplitude coming in, what fraction of it gets transmitted, so what that fraction, that's big T by definition, and the fraction, so the amplitude squared being transmitted, reflected, compared to the amplitude squared of the incoming wave, that fraction is called R for reflection. That's the part that bounces back, if you like. So we had formulas for R, big R, and big T, and R plus T is 1. Okay. Now, in the case when E is greater than V, then for your formula for T, you had a shine big Ka. Well, when E is greater than V, instead of shine of big Ka, you'll get minus I sine K dashed of A. Now do this for homework. So redefine the values of R and T. So do it yourself. Get into the nitty gritty. So that's an essential part of the learning process. So so your shine Ka will become a sine. All right. Now what's interesting about that is that if you got a sine for certain values of K dash A, for example, multiples of pi, when K dash A here, when it's multiples of pi, pi, 2 pi, 3 pi, whatever, then sine of integer multiples of pi is just naught, 0. So so when that's the case, when your sine term in your big T, the fraction that gets transmitted, so when the sine's 0, your T is 1. I mean exactly 1. Right? So that means everything goes through. So there are certain special cases when your K dash A is a multiple of pi that your big R, your reflection fraction goes to 0, so everything goes through, nothing goes back. Right? So R is 0 and T is 1. So you get perfect transmission. Everything goes through. So in a sense, you can see it as a kind of resonance effect. You know, resonance, when you blow into, say, a pop, soda pop bottle, and you blow in it in a kind of whistling way at a particular frequency. If you can find the right frequency, the bottle, this glass bottle, will resonate. And what's happening is that the wavelength of the frequency that you're whistling at fits, like a half wavelength or a full wavelength or whatever, fits into the size of your bottle, and so you get a standing wave generated by the energy of the whistling, and that standing wave will sort of reinforce your sound, and you get sort of a louder sound at that frequency, kind of resonance. So here, by analogy, is a kind of resonance effect. So for values intermediate between these pi's, you'll get some reflectivity. You'll get some R. R will not be 0, and T will not be 1. But for certain values, these multiples of pi, R is 0 and T is 1. So it's a kind of resonance effect, and you get perfect transmission. Everything just goes straight through, all of it. So that's a bit of a surprise. So you don't expect that kind of thing classically, I guess. All right. So, but you do, normally you still get some reflection, right? And that seems a bit counterintuitive classically. If your if your E is greater than the V, you think the particles go straight over. It'll just, all of it goes over. But in quantum mechanics, there's still, except in these resonance cases, whatever you want to call them, your R will be non-zero, except in these cases, right? And in the classical limit, when your E becomes hugely larger than V, so this obstacle is just nothing, pretty well, effectively, then you get the classical limit. You can show that for homework as well. But your R, your reflectivity, the fraction of your amplitude squared going back, goes to 0, right? So that's what you'd expect classically. All right, major new topic now. We move away. So up to this point, we've been dealing with one particle systems, pretty much. I mean, we've been talking about beams, but effectively, we're talking about one particle going through a system. So now, in many particle systems, we will need a many particle wave function, because quantum mechanics is all about amplitudes, and you can add amplitudes, states and statistics and probability of getting certain measurement results. For example, if you go looking for where the particle is, what's the probability that it's in a particular sub-volume or whatever, right? So if you're going to do something similar, we're going to do quantum mechanics with a multi-particle system, presumably as a kind of carryover from the one particle case. We'll need wave functions, and a Schrödinger equation that applies to multi-particle systems, all that stuff. So we expect there to be a pretty hefty carryover from the one particle quantum mechanics that we've been doing till now. So this moment now is a kind of watershed, right? It's a major change in what we're doing. We're now dealing with multi-particle systems, and that's where the real fun starts in quantum mechanics, because stuff gets weird. And then, of course, if you have multi-particle systems, you can start talking about quantum chemistry, right? You can start talking about atoms more seriously, because atoms consist of nuclei and electrons, and multiple electrons, and higher elements, with more and more greater number of electrons, and start talking about the nature of the chemical table, the chemical elements. So multi-particle quantum mechanics allows you to do all this sort of stuff. So in a sense, a vast new domain opens up when we move into many particle systems. So we'll need to find many particle wave functions. We'll need to adapt the Schrödinger equation to have a multi-particle Schrödinger equation, and so on and so forth. Okay? Right? So let's start with the simplest case. Let's say we have n particles, wavicles, and by their nature they are distinguishable. You can tell one is different from the other. You look at this one, it's different from that one. They are distinguishable. You can tell the difference between them. Well, that's obviously particle 1 by its nature, and that's particle 2, and particle 1 and 2 are different, right? And let's imagine there is no interaction, no interaction between these two particles. And let's assume now with n particles, there's no interaction amongst any of them. Okay, so each one of them is just doing its own thing, so to speak, independently of the others. So so the psi function of these n particles effectively will just be the product. If you think about it, it'll just be the product of the individual psi functions, the one particle psi functions of each one. So now what I've just said is pretty significant. Sometimes I sort of say something fairly quickly and it's like really important. So let's say particle 1 has its psi function, its wave function, psi 1. And particle 2 has its psi function, psi 2. And those two psi functions are independent of each other. Right? There's no interaction amongst the particles. This is like the simplest case. Walk before we can run, kind of thing. And similarly, the third particle has no interaction with the first two, so its psi function psi 3 is independent of psi 2 and psi 1 and so forth. So the psi, like capital psi, like here, let